One problem with using deep neural networks is that it's very hard to understand what a model is doing when that model has millions or tens of millions or hundreds of millions of parameters. So this is a general problem that we'll be focusing on later in the semester for more broad examples and applications. But today I'm going to give you a brief introduction to two techniques that help us understand how the network is classifying images. So this is often used with convolutional networks, although it may not necessarily be the case. You can use them in different networks, but I'm going to, in this case, illustrate this by focusing on image classification with these kinds of convolutional networks, because this is what we've been doing in this part of the semester. And so to take advantage of that matter that we've been covering, we're going to focus on these examples. But later on in the semester, I'm going to talk a bit more about this problem of interpretability, of understanding what these deep models are doing, and then we'll cover this a bit more broadly. But this will just be a short lecture for a brief introduction to these techniques, occlusion maps and saliency maps, that are used to understand how the network is looking at the image and classifying the image or solving the problem that we wanted to solve. Note that these will be very simplified versions of these methods, just to show you quickly how you can implement and what the results are. There are many variants and more sophisticated approach, but we are not going to cover that in depth. This is just a brief introduction. I'm also going to talk a bit about the next sessions next week and about the test on May 10th. The test will cover basically this subject matter that we've been covering until today, but I'm going to talk a bit about how the test will work and what you need to do. So let's start with the occlusion maps. The idea here is we present an image for classification. The network gives us a result. It gives us, for example, the class the image belongs to. You did this in the assignment, but what did the network look at in order to make that decision? Which parts of the image are important for that decision? We can check this by covering a part of the image with a mask, say a gray square, and then looking at what the effect this had on the classification given by the network. So basically, we can do something like this. We have an example from your Pokemon dataset, and we can generate new images by placing a gray square in different positions on the original image. And then we can look at what the network is telling us about the class of each of these new images. We should expect intuitively that covering these parts here of the background would not make any difference. If they do, then our network is probably learning something wrong. What should make a difference is covering parts of the Pokemon if the network is actually learning to recognize the specific Pokemon type. So what we can do this, for example, easy way of doing this is to create an iterator. An iterator in Python, for those of you who are less familiar with Python, is a function that instead of having a return, so the return ends the function and returns the result, it uses yield. Yield returns the result, but then you can call the function again as part of a loop, a for loop, and it will continue from where it yielded. So this is a practical way of looping through the rows and columns of an image with a step of the size that we specify. So in this case, I specified size 8. So the step here is in size 8. You can vary this. The step does not need to be the size of the square and so on. There are many different combinations that you can do here, but this is just a simple implementation. And we are going to loop through the rows and the columns and create a copy of the original image, which has a gray square in this part here. So in those rows and columns. Now note that I have an additional dimension there because I am thinking about this in the context of feeding it into the neural network, and the tensors there have 4 dimensions. The first dimension is the different examples, the different images, then the width and height of the image, and then the color channels. So I'm working with these kind of tensors with this shape to create these images with covered square in different places. And now I'm going to compute the occlusion map by looping through all the positions where I can put the gray square, using my model to predict the class of the image after this kind of transformation, after hiding part of the image. And then I'm going to look at the value of the true class. So remember, if you did this part on the assignment, the multi-classification for the Pokemon images, the output should be a softmax with the different classes. And we can look at the position of the vector on the true class to look at the probability the model predicted that this image belongs to that class. So this would be the true class of the image, and we are checking to see how that probability prediction changed when we cover different parts of the image. And now we can create the occlusion map by filling in the region. So the occlusion map will be the same size as the image, but we fill in the region corresponding to the square with the probability that the model assigned to this true class. So this print is just so we can see how the things are being computed. It's not important for the actual result. What matters is this map. So now we can just merge the two. We're going to load the models, the model we trained for the multi-class problem, for example. We're going to load the Pokemon data. I'm going to choose this image, for example, the third image. The third image is the one with this small Pokemon there. And we're going to create the occlusion map. And now I'm going to merge the occlusion map with the image by using the red channel for the occlusion map. So basically we can see here the output, the result. Whenever the red channel is at 0, it means that there was the probability of classifying this image correctly is the probability assigned to the correct class by the model is very high, because I used 1 minus the value there for the red channel. So all these areas in blue are irrelevant for classifying this Pokemon, because covering them with a square will not have an effect, will not lower the probability that the model is assigning to the correct class. But this part here and this part here will cause a drop in the probability of the correct class. So it seems that at least when we cover parts of the image, if we cover this part or cover this part, we reduce the probability the network is assigning to the correct class. And so we can infer that those parts of the image are the important part, or the most important parts for the network to identify this Pokemon. You can even look at whether or not some parts cause the network to make mistakes. You can do a more sophisticated analysis here. So this is just a very simple example. But what I wanted to illustrate is the basic idea. We are hiding parts of the image. You can use different sizes for those squares if you want, larger, smaller. And we are looking at the effect on the probability assigned to the correct class. Or you can look at different effects, the assigning it to an incorrect class, something like that. Okay, so this is occlusion mapping. It's one way of understanding what the network is doing with a given image. You can then use this for different images and look at how the network is classifying each image. Another way of visualizing the importance the network is given to different parts of the image is the saliency map. And this is a map that represents the derivative of the classification or some aspect that you want to measure with respect to the pixels in the input. So remember that when we are doing backpropagation, we compute the derivative of some loss function with respect to the parameters of the network, and then we update those parameters. But we can do the same thing. We can use auto differentiation to compute the derivative with respect to the inputs, and then have an idea of which input values are more important for that classification. So for example, if we look at the probability the network is assigning to the correct class, to that example belonging to the correct class, then if a pixel has a high derivative, or if the derivative of that probability is large with respect to a particular pixel, it means that changing that pixel will cause a larger change on the probability assigned to the correct class. If the derivative with respect to a pixel is small, it means that that pixel will not change the probability assigned to the correct class. So if we compute the derivative of the probability the model is assigning to the correct class with respect to each pixel in the input, we can have an idea of which pixels are more important for that classification, or at least which pixels, if changed, would have a larger impact on that probability. So we can do this using the gradient tape class. This is one example where, even though we are doing everything on the higher level API using Keras, it's still useful to know how TensorFlow works below that level, so that we can use these techniques. So let's create a saliency map where we have the trained model, an image, and the correct class for that image. So what we're going to do here, first, these images are going to be fed into this function as NumPy arrays, but I'm going to convert them into tensors in TensorFlow tensors so that I can apply this gradient tape. This is similar to what we saw in the first sessions on TensorFlow. I'm going to create this gradient tape context. I'm going to watch the image tensor here. I have these predictions. So the prediction is the output of the model with the image tensor. So what the model is telling us should be the probability distribution for the different classes given this input. But now I'm going to pretend that the loss function I'm following here for tracing the derivatives is simply the value on the correct class for these predictions. Note that this first dimension is because we can have several examples here. So this image can be a set of images in theory. In practice, we are not going to do that because we want a feature map for one image, but this is the shape of the tensors that the models are expecting. So now we're going to get the gradient of this pretend loss function, which is just the probability assigned to the correct class, with respect to the image tensor, which is the input into the model. This is analogous to what we did when we computed the derivative with respect to the variables that we were adjusting. But in this case, we are computing the derivative with respect to the inputs. So now we just convert this to NumPy. We rescale everything because these gradients can have widely ranging values. So we just rescale them all to between 0 and 1, and we return this saliency map. And now we can use the same trick of loading the image, I'm going to pick the same image, the same Pokemon, getting the saliency map, and then using that as the red channel on the image, so that we can overlay that with the image and see what are the important pixels. And this is the result. You can see again that pixels here in the background do not have anything on the red channel, so the derivative of the probability assigned to the correct class with respect to any of these pixels is very low, which means that you can change these pixels and the class will not change. The model will assign the same probability to that class. But there are pixels here around the Pokemon that seem to be especially important. So changing these pixels will have a larger effect on the classification. So this gives you an idea of what the network is considering important for classifying this Pokemon. Now, again, there are lots of different options here that you can consider. For example, I used the absolute value of the gradient here because I don't care if the gradient is positive or negative. I just want its magnitude. But this could be, you could want to make a distinction here between those pixels that have different kinds of values, or check the effect of the pixels on the function and so on. We also are computing the maximum for the different color channels. So for each pixel, I take the maximum gradient for all the color channels, but we could want to distinguish between the different colors to see which one is more important. Also, rescaling, we could want to do rescaling, or we could want to do rescaling differently if we wanted to compare different images on the same scale, because this will do the rescaling for each image, and that may not be what we want. So there are lots of different things that you need to consider when you're doing this kind of mapping, but the basic idea here is that we are using the gradient tape to compute the derivative with respect to the pixels, and so we get a representation of what the network is considering to be more important or has a greater impact on the probability that it is assigning to the correct class. Okay, so this was just a short lecture to compensate a bit the previous one, and to wrap up this kind of subject matter that we've been seeing lately on dealing with images and these convolutional networks. So now I'm going to talk a bit about what we're going to do this week and the next. Since you need to submit the assignment by the end of this week, we are going to dedicate the tutorials today and tomorrow just for questions about the assignment. So you have 48 hours of tolerance to submit your assignment. I can accept them until May 4, but I will suggest that you try to solve everything or do everything by May the 2nd at the latest, so that you have time to focus on the theory and study for the test and so on. But you have 48 hours of margin for solving any submission problems. Check when you send the zip file if it's the correct format, if both members of the group are sending exactly the same file. Note that if one of you makes the zip file on a Mac and the other on a PC, it will probably be different, because the Mac has some hidden folders where it keeps different information and so on. So be careful about that. Solve all those problems for the submission. In the meantime, I'm going to update the lecture notes. I didn't have time to write everything about the autoencoders, the GAN, and these visualization methods. And I'm also going to include some revision exercises for next week. So next week will be the lectures. I will not give a lecture on YouTube. It will only be for questions on Zoom. And then the exercises will be just revision exercises to help you study for the test. But note that the test will be theoretical. It will not be for writing codes or solving practical problems. The revision exercises will be just an overview of the subject matter to help understand some concepts, but you will not write codes in the test. The test will consist of 5 questions. You'll have 10 minutes to answer each question, and then there will be a 5-minute break between questions. This is the same format that we used last semester on the machine learning. The questions are not for you to do calculations or write code or things like that. They are focused on having you explain some important concepts. And the questions will include an ordered list of what is more important or less important for you to cover. And the idea is that you think about the question and the topics that you need to cover, organize a structured and concise answer. This is not a typing contest. You don't need to type much, but you need to have a clear idea of what you want to say, and you need to say it in your own words. If you copy things from the lecture notes, from the book or things like that, then I cannot evaluate how much you know. You need to write in your own words and explain how you understand the concepts. And that's the only way for me to have an idea of how clearly you understand the subject matter. What is going to be covered in the test is what we covered until today. So starting from the beginning of the semester until today. Check the site for the instructions on the test. do a few tries to see the mechanics. Especially one thing that some students make a mistake is instead of typing the login, they type the whole email address and then things go wrong. So do a rehearsal in the demo that you have online to make sure that you understand how the test works, and so that you have everything ready for the test day. Also remember to log out from any alternative accounts that you have and log into your official Gmail account before doing the test. That part is important, and many of you always forget that. So to sum up for today, before we go to the questions session, we saw in this short lecture just some simple examples of visualization methods that are used in image classification, mostly with convolutional networks, but in theory they could be applied to other kinds of models, but they are useful for this type of problems of dealing with image. Occlusion maps, we are checking to see if covering part of the image has an effect on the output of the network. For example, looking at the probability assigned to the correct class for that image. With saliency maps, we are measuring the derivative of some output with respect to the pixels. For example, this output could be the probability assigned to the correct class. We also saw a bit about the first test, the assignment, and how we are going to plan the next week. So now I'm going to log into Zoom and I can answer your questions. See you soon.